Welcome to the Visit audio playback version of the Utilizing GOES Imagery within AWIPS to Forecast Winter Storms training session. My name is Dan Bicus. Me and John Weaver put this session together. I'll be giving about half of this session, and Jeff Braun will be giving the other half. Down here at the bottom, you see the contributors that helped us out in terms of putting this session together. Our objectives are to blend GOES imagery with other available AWIPS products to help improve forecast skill and precipitation associated with winter storms. Also, we want variety, so we want to analyze case studies over various parts of the CONUS. Our topics are conveyor belt identification, and keep in mind this is a review from the cyclogenesis session that we offer, and that's the reason we say this is a prerequisite for this particular teletraining session, because we do cover that quite a bit. Also, we'll be reviewing synoptic features such as dry slot, short waves, jet streaks, things you're familiar with. Model divergence, and by that I mean when two models have different solutions, how can the satellite imagery be used in the short term to help us figure out which model is probably going to do better. Mesoscale banding, topographic effects, shear zones, as well as precipitation type, of course, with other data sets. Here's a brief review of winter weather factors. Of course, we need upward vertical motion, instability, moisture. Temperature is important, not only with respect to the snow to liquid water ratio, but also the cloud microphysics and, of course, precipitation type as well. Let's review the structure of winter storms, and again, this is a review from the cyclogenesis session where we went quite a bit into conveyor belts, the warm conveyor belt, the cold conveyor belt, the dry slot, as well as the trough of warm air aloft. And in the cyclogenesis session, we referred to the cyclonic part of the warm conveyor belt as the secondary warm conveyor belt, and the exact terminology here is that when the secondary warm conveyor belt when we start to see occlusion beginning, then we call it the trowel. And for that reason, we'll use the terms interchangeably because it can sometimes be ambiguous as to exactly when that occlusion begins. So just keep in mind that we'll be using those two terms to refer to the cyclonic part of the warm conveyor belt. Here's a conceptual diagram of what I just talked about. Here's the warm conveyor belt, and here's the cyclonic branch of the warm conveyor belt. We refer to that as the secondary warm conveyor belt, but when occlusion begins, we refer to this as the trowel. The cold conveyor belt here, pictured in blue, and then we have the dry slot or dry conveyor belt back here. Model divergence, just keep in mind here that I'm referring to different solutions between two different models. How can the satellite imagery be used in the short term to help us figure out which one is more correct in location? Here we have the MSLP field from the Eta in green and from the GFS here in salmon. And what I want to do is just go forward here in the forecast time, and you can see some differences here that have evolved in the short term. The GFS here has the low in the Nebraska Panhandle, and the Eta has the low a lot further south here in Colorado. It's important in terms of our forecast because the same trend continued out to 24 hours where the Eta had the low down here further south, and that would lead to precipitation in northern Colorado, whereas the GFS solution, if that came true, would lead to precipitation in southeast Wyoming and western Nebraska. So how can the satellite imagery be used to help figure out which one to believe here? Here we look at the IR imagery leading up to the time of the 12-hour forecast, and keep in mind that was the time when the GFS had the low in the Nebraska Panhandle, while the Eta had it further south here in Colorado. And you can see in the IR loop that the low is definitely further south, maybe even a little bit further south than the Eta, but definitely the Eta seems to be doing better than the GFS here in terms of the position of the low. The consequence of that, again, remember, was the low being further south here throughout the forecast period, which would help to give more precipitation here to northern Colorado. And that's indeed what happened. That low was further south, closer to the Eta solution here. Here's the average snow to liquid water ratios from 1971 to 2000. This is a study done by Marty Baxter of St. Louis University, and you can see the variability across the U.S., the higher snow to liquid water ratios as you'd expect in the Rocky Mountain region here, as well as associated with lake effect snow here downwind of the Great Lakes. I'm going to the next frame here, and if you click on the Show URL button, what you'll get is a link to the web page that has the map, and what you can do is scroll across the CONUS here, and you'll see each CWA, and what you do is just scroll across it, and you'll see something like so. Here's an example from the Denver Boulder CWA, and what it will give you is the average snow to liquid water ratio, the standard deviation, various percentiles, how it varies across the CWA, as well as this frequency diagram down here. So this is a good thing to keep in mind for your CWA before the event begins. Just gives you an idea of what to expect climatologically. Next topic is the satellite shear zone. We're referring to an open wave aloft with a strong speed shear along the jet and a vorticity maximum elongated downstream. This is most reliable when there's a long, narrow dry slot. There's two types of shear zones. The stationary one, which is stationary with respect to the trough axis, and the example is going to be shown next. There's also another type that rotates with the trough axis, and that'll be depicted in a case study we'll show later. If you want more information about this, there's a paper referenced on the student guide that you can look at for more information. Here's the example of that. We're looking at the IR imagery, and remember what we're looking for is a long, narrow dry slot, and in this example we see it going across Washington, Idaho, into Montana, and the idea is that you look just north of that, where this cloud cover is, to tell you where the shear zone is in terms of where the most snow is occurring here. In this particular example, we have a couple different vortexes. One elongated the furthest downstream, the one that's typically there, and this one's moving across British Columbia. And then in this particular case, there's another one further east, just north of Montana here.
This is Jeff Braun. I'll be taking you guys out to the high plains and Rocky Mountains of Colorado for the first case here. We're going to be looking at the Denver Boulder CWA for March 17th through the 20th of 2003, and we'll be forecasting for a 12 to 36 hour time period starting on the morning of March 17th. The objectives for this particular case are going to start out with identifying important synoptic and subsynoptic elements, to blend satellite and numerical weather prediction models together to improve the forecast, and to show just how satellite data can be utilized to give added extra value to forecast situations. We're also going to look for clues for the rain-snow changeover and the effects of the topography around the area. Here's the Eta 300 millibar height and ice attacks from Monday, the 17th at 12Z. Shows the approaching trough, and by 0Z, the trough really becomes negatively tilted, and 6 hours later, we've got a cutoff low on our hands. Another thing that I want you to notice that by 6Z, we're also trying to force a little weak jet max up in northeastern Colorado area, while the stronger portion of the main branch of the jet underneath the trough is flowing well to the south at this time. Here's the Eta 500 millibar height and vorticity field from 12Z on the 17th, showing the 12 through 36 hour forecast. I'll loop it through here a couple times to show you what is expected to happen over the first 36 hours. We notice that by the first 12 hours, we have a fort lobe sitting over the northern Texas panhandle around the Dalhart area. And as we move forward another 12 hours, that is forecast to move into the eastern portions of Colorado. Very important for what we're going to be seeing here later on. We also want to notice that during this time frame, the first 24 hours, the low is forecast to consolidate, deepen, and move into eastern and southeastern Colorado. Here's the mesoeta surface analysis showing sea level pressure, precipitation, temperature, and winds, also from 12Z on the 17th. Surface low at the beginning of this is in southeastern Colorado. The urban corridor with Denver and Fort Collins lies in this area, with the mountains adjacent just to the west in this area right here. As we move out in time, we'll notice that we have a deepening low that's moving through, and you combine this with the 500 millibar and 300 millibar analysis from previous slides. It shows that the entire low extends to nearly the depth of the entire troposphere. Northeast Colorado is also forecast to keep deep upslope flow over the entire period, and the output shows an area of precipitation throughout north central Colorado for almost the entire period. Another thing we want to take notice of is that the freezing line remains just along the foothills area, but mainly to the west and up in the mountains, except for southeastern Wyoming, which is forecast to be at or below freezing for most of the time period. If we looked at the thickness analysis, which isn't shown, it also shows that the rain-snow line is forecast to remain approximately at the 6,000 foot mark during the entire period of time, so that if snow does occur, it will be heavier than the climatological 15-to-1 ratio that was shown previously. Heavier precipitation is forecast to develop over Oklahoma and Kansas by 0Z and expand with time through 12Z into the Colorado area. Here we're going to look at the water vapor loop from 430Z on the 17th through 0Z on the 18th. And we're going to try to see how satellite imagery can be used to add extra value to the model forecasts. Here, as we start the loop, we notice that the warm conveyor belt moving up from Oklahoma and into central portions of Nebraska. We want to notice also that we have an area of deep convection from south central Kansas in through Oklahoma. And what does this mean in the warm conveyor belt? It means that the low is going to deepen as we further push more energy into the system. We also want to notice the short waves that are moving through in the jet maxes. So we want to pick those out. Those are subtle. One of those we'll look for at the beginning of this loop, moving from north central areas of New Mexico into eastern portions of Colorado, which we noticed on the forecast. So that matches up pretty good. We want to notice another area moving from northern Arizona into northern New Mexico during the same time frame, while at the very base of the trough we have a strong jet max moving in here, and we can see results of that at the very end of the loop. As I move it up here into West Texas, we see this area developing in here that which should forecast to move up around the base of the trough and perhaps be important later on. Here's the mesoeta forecast analysis for the 310K potential temperature surface overlaid with pressure, winds, and relative humidity, also from 12Z on the 17th. The ETA is showing weak isotropic lift over northeastern Colorado at the beginning of the time period. As we move out 6 hours, it shows the strongest areas of isotropic lift to be right over the urban corridor in the mountains that we were talking about, and we move out an additional 12 hours, and by that time it's moved into northwestern Colorado and has weakened significantly over our area here. Here's a slide showing model output for 0Z on the 18th, showing a few model differences. The ETA model is sitting here in southeastern Colorado and matches up quite well with what we've seen previously, while the NGM is much further north, almost northeastern Colorado. If the NGM ends up panning out, that would force precipitation more into eastern and southeastern Wyoming, while the ETA model has the bulk of the moisture in the upslope going into northeastern and north central Colorado. What we'll end up doing is looking at the visible imagery to match up and to see which model is better in this case. Here's a GOES 10 visible imagery loop showing the low in extreme southeastern Colorado. As I animate that, it shows that the Ada was much better and more accurate in its sea level forecast than the NGM, and is a good example of how to verify model initializations. Here we see some Colorado topography. With the low sitting in southeastern Colorado, we notice that the air will be moving around from the east and undergo forced lift, and this roughly equates to 3,500 feet as it moves from the Colorado border area to the Front Range. Also, as the low-level air encounters the mountains, it will be partially blocked. This effect causes the boundary layer along the foothills to deepen and flow to accelerate to the south during that same period of time. Remember that the flow through the whole mid to lower troposphere was easterly as well, implying that the upslope was much deeper than the mountain barriers in this particular case. In normal upslope, it's usually shallow and the upslope is contained by the mountain barriers, and snow only exists east of the Front Range area. But in this particular case, the flow was very deep and actually rode over the mountain barrier, providing significant chances for these areas back here to the west of the Front Range. Here's the Ada surface analysis showing sea level pressure and precipitation from 12Z on the 17th, running out to about 18Z on the 18th. I want to notice as we loop this forward that the precipitation band stretches from Kansas across southwestern Nebraska and wraps back around into north-central Colorado. Also note the forecast position of the surface low, which in this case is pretty good with what we've seen previously. We can use this to compare the position of the low with the surface obs and also the precipitation forecast with the infrared satellite data to get an idea of how well the model is doing. In this case, the surface low position is pretty good. However, the precipitation forecast seems to be a little bit too far to the north. So here are the surface observations from 0Z through 5Z on the 18th. This surface analysis for early through late evening shows pretty good agreement with the meso-Ada as far as the winds are concerned, but the temperature forecast, as we look at a loop of this, turns out to be a little bit high over the north, central, northeastern, and southeastern Wyoming areas. Also note the strong northerly winds developing along the Front Range. This is a result of the barrier jet. The barrier jet causes the boundary layer to deepen and the winds to accelerate as they are deflected to the south. Throughout the evening hours, temperatures remained in the low 40s and high 30s along most of the northern Colorado Front Range. However, in southeastern areas of Wyoming, the observations showed that the lows were in the low 30s or below most of the afternoon and through the evening. Note the intensifying northerly winds and changeover to snow in both Laramie and Cheyenne by 1Z. Also notice that the low pressure and circulation center indicate that the low is in reasonable agreement with the Ada at this time. It turns out that the changeover from rain to snow took place along the Front Range cities above 5,000 feet and around 5Z. Note that this will also be the time of the arrival of the shortwave, as we will see on the infrared image coming up next. Here's GOES 12 10.7 micron infrared loop from 2015Z on the 17th that runs through 6Z on the 18th. Early in the loop, we can see the north-south bands of colder cloud tops in north-central Colorado. These tops were associated with north-south oriented squall lines. The convective lines can be seen here moving into northeastern and north-central Colorado from east to west in this case. From 230Z to 530Z, the shortwave moving into Colorado from the southeast causes the aerial coverage of the colder cloud tops to expand due to upward motion. And notice that the cloud tops associated with the warm conveyor belt now extend from southwestern Nebraska through northeastern Colorado. During this time, the precip along the Front Range was rain or rain mixed with snow. If we remember back, we had the Ada was showing that the warm conveyor belt was further north and east But the satellite clearly shows that the warm conveyor belt is a little further south than forecast. As the shortwave moves into the Front Range, the precipitation area broadens and precipitation rates increase dramatically. Also notice the shortwave observed in West Texas that we talked about earlier continues to expand in aerial coverage and it moves to the north-northeast. Now we're going to look at the strength of shortwave on profiler data. Here is some profiler data from Platteville, Colorado, starting at 19Z on March 17th and running through 7Z on the 18th of March. A reflection in the change of the wind structure and dynamics can be seen in the vertical wind structure as the shortwave moves in. This corresponds with the warm conveyor belt enhancement noticed on the infrared imagery previously. The winds at all levels increased substantially between 2 and 4Z. Between 5 and 5:30Z, observers from Fort Collins through the Denver area reported the changeover from rain to snow, and this is coincident with the arrival of this disturbance. The changeover probably occurred as a result of the continuous and deeper precipitation layer. With precipitation falling from higher levels, there would be greater cooling at the lower levels. Here's a loop of radar imagery taken at a half degree from the time period of late Monday evening through early morning Tuesday on the 18th. As we loop this forward, we notice that between 0Z and 230Z, the precipitation takes the form of discrete north-south lines of intense convection, during which some severe weather was observed, even a small tornado reported just east of Denver. The convective lines were associated with periods of relatively heavy rain along the Front Range. Then, beginning shortly after 230Z, precipitation becomes much more widespread, and this is associated with the arrival of the shortwave that we've been talking about previously, and the enhanced warm conveyor belt. Transitions to snow began between 5 and 5:30Z along the Front Range. Notice the small circulation moving in from the southeast into central portions of Colorado. This was a small wave that moved up from New Mexico and was referred to in the water vapor imagery at the beginning of the discussion. Now we're going to look at a GOES water vapor loop from 030Z on the 18th that runs through 12Z on March 18th. As we loop forward, notice between the hours of 11 and 12Z, thick clouds associated with the first period of heavy snow as they move off quickly to the northwest and then weaken. Fort Collins had an average of 8 inches of snow reported with this first precipitation by 14Z, and this snow fell at a ratio of 6:1. We also want to notice the dry slot moving in the northeastern Colorado and along the Front Range. What is this going to mean? Is this the end of our snow? And finally, we want to look at the area in western Texas where the shortwave and jetmax is moving into. We have enhanced convection from northern Texas in through western Kansas. What will this do? We'll find out in the upcoming slide as we look at the infrared imagery. Now we're going to look at the GOES infrared loop beginning at 10:15Z on the 18th, running through 1:15Z on the 19th. We can see new convection starting late from where the previous loop left off, and we see now that it is indeed associated with a second shortwave and an invigorated warm conveyor belt. The intensified warm conveyor belt moved into northern Colorado during this period, leading to a long duration of heavy snowfall starting around 19:30Z on the 18th and continuing through the early morning hours of the 19th. The key in this case was holding the low in place and allowing heavy snow to begin again and continue for an additional 24 hours. Finally, here's a GOES infrared loop for the entire event. This loop starts at 0Z on the 18th and runs through 0Z on the 19th. Remember that the imagery tracks the development and movement of the warm conveyor belts and provides nowcasting guidance for the beginning and ending of various phases in this event. The Eta represented the first and second shortwave, along with the warm conveyor belt discussed, fairly well. However, in both instances with the shortwave, the model had the maximum amount of precipitation associated with the features too far north. The role of satellite data here is critical, as you can see how the Eta forecast precipitation fields were evolving, and you could adjust your forecast positioning and consequential QPF amounts by utilizing both satellite and models in tandem. It should also be noted that Denver National Weather Service handled the situation rather well and stuck to their guns, forecasting the changeover from rain to snow. Also, it was critical in this particular case that the changeover from rain to snow occurred also as a consequence of the increase in precipitation, which the satellites showed well, but the models again had too far north. The increase in precipitation cooled the lower levels quicker and caused a quicker changeover to snow, resulting in larger and deeper snow amounts. And here is the snowfall totals. The satellite data in this case helped confirm and even deny certain aspects of the model output. The snowfall pattern also clearly shows the role that terrain played in this event. So in summary of this particular case, we want to particularly take notice of the synoptic and subsynoptic elements, particularly the position of the low and the short waves, the evolution of the worm conveyor belt, and the satellite data used to monitor the Eta QPF and any other model fields, and to be able to adjust the forecast position and the precipitation amounts accordingly. We also want to take notice of the precipitation type, as the deepening upslope with the arrival of the short wave caused increased precipitation, cooling the lower levels off faster, and thus we had a changeover from rain to snow a lot quicker. We also want to take into account the effects of topography, particularly noticing the formation of the barrier jet along with the increased depth of the upslope.
Our next case is from 16 to 18 February 2003, and we'll be forecasting for the shaded area here with a special emphasis on the New York City area. Our objectives here are to look at the conveyor belt evolution and effects, the position of a surface high, which was pretty important in this case, as well as a low that developed off the coast, identify a deformation zone and follow its evolution as well. We also had a pretty significant trowel, and I'll talk about dry slot identification in this case as well. Let's start off looking at some model output. This is the Eta 300 millibar isotax shaded, and the height in yellow. And you can see this jet here in the northeast. We have this confluent zone in southeast Canada and into the New England states here, and that's typically present before these big nor'easters. Typically what that does is help keep that cold high pressure system at the surface in place, and I'll show you the high at the surface here in a little bit. Also, that will help delay the system as well with that high pressure system in place. So let's advance forward in our forecast time here, and we can see by this time right here as this significant trough is developing and moving towards the east. We have a couple different jets, the one I just mentioned before to the north, and then another one down here off the South Carolina coast, which puts the New York City region in between two jets here. And then as we move off in time here, we can see that move to the east. Next, let's go to the 500 millibar heights in green and shaded as vorticity. And the main point I want to make here is just that we have a very significant trough over the eastern U.S. and moving towards the northeast. So this definitely looks like a major event here. We'll start looking at some lower levels here next, and then we'll start looking at the satellite imagery. Before we get to the low-level model fields, let's look at the terrain here first. And typically what happens is we have that surface high pressure system somewhere to the north, and that helps keep the cold air just east of the Appalachians, something like this. and it generally follows just east of the Appalachians here, where that precipitation type changeover occurs. In other words, it generally follows one of these terrain lines here, depending on the setup, of course. In terms of the New York City area, a couple things that they look for in terms of the low-level winds is that if the low-level winds are coming off the ocean here, pretty much out of the east, that's off the ocean, and probably too warm to get snow there, more likely to be rain. And then if the winds are coming from the north here off the land, they're more likely to be snow if it's cold enough. So the low-level wind direction is pretty important as well. Also, another thing to consider is flow down these river valleys here, the Hudson and Connecticut river valleys, where if you have pretty cold air mass in place there, you can actually get some very cold air draining down these river valleys towards their region here. Now let's look at the Eta 12 QPF, which is shaded. MSLP is in green, and then we also have the wind barbs on here. And we can see at this time that strong high to the north, about a 1047 high here over southeast Canada, and that helps keep that cold air just east of the Appalachians. You can see the northeast flow helping to keep colder air banked up against the Appalachians here east of West Virginia into Virginia and so forth. And what I'm going to do next is just advance along in time here, and you can see the system slowly developing. Here it is, 10-12 millibars just off the coast of North Carolina at this time, and slowly moving its way towards the northeast. And you can see the significant QPF associated with it as it moves slowly to the northeast. Also keep in mind, during that whole period, this high is still to the north here, which makes for a pretty significant pressure gradient in the vicinity of that low, and therefore strong winds helping out frontogenesis, and therefore pretty heavy precipitation event heading for this area here. Now let's look at the water vapor imagery, and a few things to point out here. First of all, I'll go ahead and stop the loop and identify a few of the conveyor belts that we're reviewing. First of all, the warm conveyor belt running something like this. And also, one thing about this warm conveyor belt here is it's actually drawing in air from the subtropical region, where you can see it coming in from off the map here. So pretty moist air going into this system here. And let me advance forward a little bit further, and we start to see the cyclonic branch of the warm conveyor belt develop right about this time here, where we see that secondary warm conveyor belt like so. Cold conveyor belt coming pretty much in this direction here, and where these two intersect right over about Missouri or Illinois, you can see this deformation zone set up. So let me take away my annotations and move on here, and you can see that deformation zone set up across Missouri, Illinois, back into Indiana. So in other words, this region right in here, we see this deformation zone, and it's moving in a storm relative sense to the northeast here. And of course, that's something to monitor as it gets closer to the northeast here. Deformation zone, obviously, one of the ingredients for mesoscale banding, so something to monitor. Next, let's look at the IR imagery, and here we have the IR imagery overlaid with the MSAS analyses. So we have MSLP in the green contours, and we also are looking at surface observations. Note here early on with that cold high pressure system to the north, we have a very cold, very dry air mass in place over the New England region here, with dew points around -10 to -20 here. And the effect that would have is that the snow is pretty slow to make it towards the northeast here. In other words, we have to have some precipitation into this dry air, and it'll get to a point where it'll eventually start reaching the ground. But also, because of that gradient in dew points, there will be a pretty tight gradient in terms of going from no snow to fairly heavy snow. So as I advance along here, you can see the snow slowly move towards the northeast here. And we start to see that low come into play here just east of Virginia, getting near the end of this loop. And then by 18Z on the 17th, which is right here, we see that low, according to the MSAS analysis, just east-southeast of Delaware by this time. Next, we'll look at the water vapor imagery here, and several things to note. First, that warm conveyor belt that we see, again, with a tropical connection from points further south here off the screen, bringing up moisture from the subtropical region. Also, we were following this deformation zone on the northwest flank of the cyclone, and in a storm relative sense, it moves right towards our forecast region here, towards New York and into the New England states here. One other thing I want to point out is the dry slot. So what I want to do is stop the loop and go to the point where we first see the dry slot developing. If we loop back and forth here, we can see that dry slot first impinging on the warm conveyor belt right in here in Georgia. And then what we can do next is just simply draw a line from that point and extrapolate it to where we believe it's heading, just based on the short loop that we saw right in here. So what I'll do is animate the loop here, and you can see that dry slot is pretty nicely extrapolated by the line here. And another thing you can do is draw in tick marks in terms of the timing when that dry slot will come through. If you're forecasting here for Boston CWA in eastern Massachusetts, you can see that that dry slot is probably going to be just east of your CWA, and therefore we will keep up that snow during that period there. And one other thing I want to point out near the end of this loop here, I'm going to stop it and then go to, see right here, I want to focus your attention on North Carolina right in here. Notice these cloud elements moving towards the west that have developed, moving this direction here. As I advance forward, you can see those developing and moving off towards the west, and as I advance forward a little bit more, we can see that that's actually a cusp that's developed right across Virginia, right in here. And remember to look for the low pretty much east of that cusp after you first see it. So the low being just east of that cusp, right about here. And that agrees pretty well with the MSAS analysis that we saw, placing the surface low just east-southeast of Delaware there. So again, in review, we identified the various conveyor belts here. We also noted the deformation zone on the northwest flank of the cyclone, moving towards our region of interest here. And also we looked at the dry slot and saw that it was going pretty much in this direction here. Next, let's look at the mosaic of radar reflectivity over the region here. And you can see the system was moving fairly slow towards the northeast. Remember, there's a pretty significant high up here, and the low was slow to make it towards the north here. And you can see the precipitation here slowly moving towards the north, and quite a bit of precip just north of Long Island into Connecticut and southern New York here. And that's actually some mesoscale banding that's set up for some period of time here and provided for a little bit higher snowfall amounts locally. Also, one other thing to point out, by the end of this loop, notice this persistent band that sets up in upstate New York right over here. And remember that deformation zone we had been following on the northwest flank of the cyclone that moves into this region and helps to reinvigorate this mesoscale band here across upstate New York. And it actually persisted for quite a period of time and led to some locally higher snowfall amounts further away from the coast than you might suspect if you were just looking at these regions here very close to the coast. Let's go to the IR loop here, pretty much in review, and just go over the things we talked about. First of all, the warm conveyor belt with its tropical connection feeding into this system. Also, remember, we identified the deformation zone at the intersection of the cold conveyor belt and the secondary warm conveyor belt on the northwest flank of this cyclone. And right behind that, you can actually see a shortwave following behind, and generally that will help keep the deformation zone going here as it moves in a storm relative sense towards the northeast here. Also, the forecast implication of that being that it would help get these mesoscale bands going here, as we saw in the radar imagery across upstate New York for a period of time, and led to some locally higher snowfall amounts a little bit further away from the coast. Here's the snowfall totals for this event, and we can see very heavy snowfall amounts near the coast here. And just recall the long period of fairly high reflectivity near the coast here. We also see this region further northwest away from the coast where they had quite a bit of snow as well. And keep in mind that's the effects of that mesoscale band that we saw coming along. And again, by monitoring the satellite imagery, you can see that coming in terms of the deformation zone and have a greater situational awareness in terms of the fact that this mesoscale banding here is going to set up just a little bit further away from the coast and lead to some locally higher snowfall amounts further away from the coast where this area really got hit pretty hard. So in summary, we looked at the conveyor belts, we followed their evolution and especially the effects, what effects they were having. Position of the surface high was pretty important. It played a role in terms of keeping the cold air in place and also keeping that system from moving too quickly. We identified deformation zone and followed its evolution, and we saw that played a pretty important role here. We also looked at the dry slot and followed that along. That's one thing you can definitely use the water vapor imagery for in terms of extrapolation, where it's going to go, and get an idea about timing as well. Okay, our next case study is from 5 to 7 December 2003. And for this case study, we'll be looking a little bit further north into the New England states here, pretty much the area shaded in green that we see. Our objectives for this case are to look at the role of jet streaks and shortwaves in system intensification. In other words, what features can we see in the satellite imagery that are leading to this system intensifying? We'll assess coastal frontogenesis qualitatively by looking at the imagery. Position of the surface high, again, surface high pressure system was pretty important in this case. Deformation zones and mesoscale banding was also pretty important in this case. We'll start off once again with the Eta 300 millibar ice attack shaded and the heights in green. And again, we see this confluence zone over the northeast, which helps keep pretty significant surface high pressure system in place here. And as I go forward in time here in the forecast, we can see this jet coming along in Missouri into Tennessee, helping to carve out a large amplitude trough. By this time right here, you can see a pretty significant jet that's developed and is forecast to nose right towards the New England region here. Pretty good defluence at this time here over New England as well. And by the end of this loop, you can see a large amplitude trough forecast to deepen and move slowly towards the east. Now let's go to 500 millibars, where we're looking at the vorticity shaded and the heights in green here. And again, I'll go forward in time, and you can see that short wave coming across Missouri into Kentucky and Tennessee, helping to develop a very significant trough here across the eastern U.S. So again, the models here indicating a very significant system here. How can the satellite imagery be used to see what specifically is going to help intensify this system here? How can we track it? Let's start off by looking at the water vapor imagery. And what we'll look at here first is across the southeast. We can see some colder cloud tops across North Carolina into Virginia and South Carolina here. And this is actually a front. We have some overrunning precipitation occurring, some areas getting rain, some areas further to the west getting snow. And what happens is you can see this jet coming across the southern plains and then moving towards the southeast. And as that moves and interacts with this front here helps to intensify the system somewhat. Now let's turn our attention here further west to the northern plains. Here's this shortwave that looked pretty significant on the forecast output that we just looked at, moving towards the southeast here. And again, remember that's forecast to come around and help really deepen that trough here over the eastern U.S. Next, let's look at lower levels. Here's the Eta MSLP in the green contours, along with the winds, and QPF is shaded here. Here's that precipitation across the southeast that I had mentioned. And what we're going to do is just forecast, go ahead in the forecast time here. And we can see a couple different lows by this particular time. One low just off the North Carolina coast, and then another one over Indiana, over approximately the Ohio River Valley here, with some precip associated with it as well. And as we advance forward in time, you can see for quite a period here, this low just off the coast, and this low to the west here, with this one starting to become the primary low here off the coast, and also note, just like our previous case, a pretty significant high, keeping that cold air mass in place here over New England. Let's advance forward in time, and we can see by this time the low to the west pretty much goes away, and we have now a primary low along the coast. And as we go forward in time here, it moves slowly towards the northeast, and we see a shield of pretty heavy precipitation here over our forecast area. Now let's analyze the potential for mesoscale banding, and in order to do that, we'll look at the Eta 850 to 700 millibar layer 2D frontogenesis, which is shaded, the 700 millibar deformation, which is the dashed yellow contours, isotherms at 700 millibars in the dashed red, and then heights at that level in black. And what I'll do is advance forward here to the time of interest when the snow was forecast to really get going over our forecast region here. And what we want to look for the potential for mesoscale banding is a juxtaposition of on the warm side of the frontogenesis maximum co-located with deformation maximum, and we have that pretty much over this area right in here. And if I go forward here in time, you can see that how that area shifts to pretty much right in here across Massachusetts, Connecticut, and into New York. Another thing to look at is the isotherms. That gives you a general idea of the orientation of the band. And you can see at this time right here, they're forecast to be pretty much east-west. And then as we go forward in time here, the Eta is forecasting a change to more of a north-south orientation of the bands by this time right here. And right here we have our deformation max, or I should say our frontogenesis maximum. And we want to look on the warm side of that, co-located with the deformation zone maximum right in here. So approximately in Connecticut and central Massachusetts is forecast to be a potential for north-south oriented bands by this particular time. Next, let's look at the surface analyses from HBC, and we see our coastal front right here, just off the South Carolina, North Carolina coast, with that low over the Ohio Valley right here. Let's advance forward in time here, and you can see, much like the Eta had been forecasting, two different lows, one to the west here over the Ohio Valley, and another one just off the Carolina coast. And we'll go right up to the end of the loop here and see, again, that low just off the coast starting to become the primary low, as this one will slowly move towards the east and merge with it. And again, the persistent high to the north here, keeping that cold air in place, and also slowing down, keeping this low from moving too quickly. Next, let's go to the IR loop. And first thing I want to point out is something pretty interesting here in terms of a qualitative assessment of the coastal frontogenesis. So let's stop the loop and look early on. And go back and forth here, we can see these low-level cumulus clouds coming off the coast, and as you know, that's a sign of cold advection coming off the land here, and then picking up the sensible and latent heat fluxes over the ocean and forming these low-level clouds moving towards the southeast. And as we go forward in time, as this coastal low starts to take shape here, notice those low-level clouds in this sector down here turn around from moving towards the southeast and actually start to move towards the northwest. And I'll go back and forth a couple times so you can see that pretty well here. So what we have is the coastal front starting to take shape here, and therefore warm advection starting to take shape right in here. And as we continue to go later on here, that warm advection area actually moves offshore and becomes enshrouded in the clouds. But the point I want to make is that you can use the satellite imagery to give you a qualitative assessment of the coastal frontogenesis that's taking place. Now, the main point I want to make in this is to look at the various features here that help lead to system intensification. First of all, we see a jet that moves across Tennessee, and what I'll do is stop the loop and highlight that right here. Moves across Tennessee and moves towards the coast here, pretty much in this direction. And you can see a flare up here in the convection as that shortwave reaches the front here. And then a little bit later on, let me erase that, we see another jet come across right here, and first makes itself known right across Virginia here, moves quickly towards the coast here, and soon after it interacts with this front, which is approximately in this location right here. We'll see another flare up in the convection a little bit later on. Another thing I want to point out is this rotating type of shear zone across Illinois moving into Indiana. Remember earlier we talked about shear zone in our example where it was pretty much stationary with respect to the trough axis. And this one you can see it's actually rotating with the trough axis. And I'll go back and forth to point that out as it moves from Illinois into Indiana and Ohio. And as you may suspect, as this eventually moves offshore and interacts with the coastal front out here, this will again help to intensify the system. Next, I want to overlay some model output here, and this is actually just an analysis from the MSAS. And what we have is the 850 millibar theta E, then the black contours, as well as the winds at that level here. And you can see the warm advection pretty strong over here just east of the coastal front, and then cold advection on the back side here, as you'd expect. And the point I want to emphasize here is that as these short waves come along here and interact with this this unstable air here near the coastal front, there will be a flare-up in the convection, and therefore the system here will start to intensify as we get more and more short waves that we start to identify interacting with this area off the coast. Now let's go to the visible loop, and what I want to do here is just increase the speed of the loop and rock it back and forth. And you can see the warm conveyor belt very well defined here just off the coast with quite a bit of convection in it. You can also see the surface low here pretty easily just east of Virginia. You can see the higher clouds associated with that jet streak as it moves from Tennessee across Virginia here. And also we see that rotating shear zone across the Ohio Valley right in here. And that's slowly moving towards the east, and again will eventually move offshore here and help to intensify this system. Now let's look at a pretty long radar mosaic here. And the thing I want to point out first is the area of precipitation here in Virginia, Maryland, as it moves towards New Jersey. You can see pretty high reflectivity values. Keep in mind the rain-snow line was something like this, so that these higher reflectivity areas that you see just east of that line are actually rain, and snow being just northwest, pretty much of that line that I drew in there. The other thing I want to point out is this shear zone. Remember, we tracked it there across Ohio, and we'll see by the end of this loop, it'll move out of Ohio into West Virginia, right around there, into Pennsylvania, and you can see a definite enhancement to the precipitation echoes there across West Virginia and Pennsylvania, right around there. Now, we'll be monitoring that as it makes its way towards the coast here. Now we'll look at the water vapor imagery, and keep in mind we're looking at the short waves that came along and helped to intensify the system. You can see that one that came pretty much out of Tennessee here across Virginia and moved out over the ocean, interacted with the front, and you can see a flare-up in the convection, and definitely an intensification to the system overall. Also, this rotating type of shortwave that we identified earlier coming out of West Virginia and Pennsylvania, as we saw in the radar mosaic there as it moves offshore, that also contributed to some system intensification here as well. Now let's go to the visible imagery here, and you can see the low here very well defined just off the coast with a whole lot of convection again in the warm conveyor belt. And another thing I want to point out is this area right up in here, the potential for mesoscale banding. Remember earlier we looked at some ADA output, and it looked like mesoscale banding was forecast for this region that I just circled in here. So next, let's look at some a radar loop and assess that potential. Okay, here's this radar loop, and we can see that that potential for mesoscale banding is definitely coming true. We see early on in the loop that there were some mesoscale bands just north of New York City, pretty much east-west oriented, right around there. And then in time they became northeast to southwest oriented, and then eventually right around here we have a persistent north-south oriented band in the Hudson River Valley, and we also have mesoscale bands up here into New Hampshire and Maine as well. Also note the persistent higher reflectivity here in eastern Massachusetts, and pretty much following along the coast there, some places that got pretty heavy snow with this system here. Here's the IR loop pretty much in review, and remember the first thing we looked at was a qualitative assessment of the coastal frontogenesis, as we saw early the clouds indicating cold advection and then a transition to warm advection just east of that coastal front as that was developing. Also, we looked at various short waves that came along and interacted with the coastal front and helped to intensify the system. The first one we saw moving across Tennessee into the Carolinas, then another one that came across Virginia here, and then finally that rotating shortwave that came across Indiana, Ohio, into Pennsylvania, and then eventually it came offshore. Let me stop the loop and highlight that as it came offshore here. You can see pretty much when it came offshore right around here. We're looking in this region here, and then let me move the mouse cursor, and just as it moved offshore we can see that low really take shape right there in the imagery and move off towards the northeast there soon after that happened. Also in the imagery near the end you can see signs of that mesoscale banding over this region here as well. Next, let's look at the precipitation that actually fell. This is the liquid precipitation. There was some missing data here over Ohio, but you can see quite a bit of precip here. And then later in the period, a whole lot up into New England states here. And keep in mind, some of this was rain very close to the coast as well. Next, we'll look at the snowfall map. So to summarize this case, we looked at the role of jet streaks and shortwaves in system intensification, a qualitative assessment of coastal frontogenesis. Deformation zone was very important in this case as it led to mesoscale banding as well. Our next case study is from Riverton, Wyoming, which is shaded in green here, and this is from 29 to 30 October 2003. our objectives in this case are to look at the position and intensity of a pretty intense upper-level jet. Topographic effects were pretty important in this region, things like upslope flow as well as radar beam blockage problems. And mesoscale banding was also important in this case as well. Here's the water vapor imagery, and this is the example I showed earlier when I was introducing the shear zone, and you can see here's that long narrow jet going through Washington towards Montana, and just north of that being the shear zone. But in this particular case, since we're looking down here at Wyoming, the most notable thing you see here is this jet that's moving towards the southeast, right towards Wyoming here. Also noticed by the later half of this loop, a short wave coming into Oregon, and what I'll do is just stop the loop and go to the end of that, and you can see that short wave moving into Oregon here by the end of that loop. Now let's go to some model output from the Ada. This is the 500 millibar heights in green and vorticity shaded, and keep in mind that water vapor loop I just saw led up to the 0Z time, which is right here, 0Z on the 30th, and what we saw in the water vapor loop was that jet moving towards the southeast, towards Wyoming, vortmax associated with that short wave moving off towards the northeast, and then that short wave that was coming into Oregon right here. Now if we continue out in the forecast time, we can see that that vortmax really holds back west of Wyoming here. A piece of it comes off towards Idaho into Montana, but you can see the main trough is holding back to the west the whole time. It never really comes into Wyoming during this time period. Now let's look at the 300 millibar ice attacks shaded here and the heights in green, and you can see at this time the jet max over Montana, and that's forecast to move towards the southeast. This is the ending time of the water vapor loop that I showed. And if we go into the overnight hours, you can see the jet max really taking shape here over northern Nevada into Utah, and then during the day, the next day, it's pretty much right over our CWA here in Wyoming, and that continues throughout the day here with the main trough holding back towards the northwest. Terrain is pretty important in this area, and what I want to do next here is just show the terrain map. Riverton is located right here in a somewhat lower elevation basin with high mountain range to its southwest. This is the Wind River Range, and then another mountain range to the northeast here. Now what I want to do is animate and turn on the winds that are forecast for the middle of the day, the next day, 18Z the next day here. And the thing I want to illustrate by showing this is the areas that are preferred in terms of upslope. So we look at pretty much a northeasterly flow across the Riverton area, and therefore that would lead to pretty good upslope across this Wind River Range right here, as well as areas south of Riverton and southwest of Casper as well. Now let's look at the forecast from the Ada here. This is the MSLP in the yellow contours, surface winds, as well as QPF, which is shaded. First thing to notice here is the cold front coming in this direction through north-central Wyoming. And by the evening hours, we can see the cold front being just east of Riverton CWA. And then as we move into the evening hours, you can see that cold air moving in pretty much through this way because of the terrain. And then soon after that, this is at 6Z on the 30th, soon after that, which would be the early morning period, we see snow break out over a pretty good portion of the Riverton forecast area. And notice also as we move into the next day here, the low down here in Utah with a high up in Montana, which sets up a pretty good pressure gradient across Riverton CWA here. And like I said, pretty much northeasterly flow across the area, pretty good upslope flow across the area, so that's what we would watch in terms of locally higher amounts. But you can see the Ada here does have a pretty good snowfall forecast over a pretty large area. Now, we talked about the potential for locally heavier snowfall amounts due to upslope flow, but also let's consider the potential for mesoscale banding. So let's advance forward to the time where the snow was forecast to start early in the morning hours, right about here, 9Z on the 30th. And what we're looking at here, shaded, is the 500 to 700 millibar layer QG frontogenesis. In the yellow contours, we have the 600 millibar deformation. And remember, for the mesoscale banding potential, we're looking at the warm side of the frontogenesis maximum corresponding to the same location as a deformation maximum, and we can definitely see that right here across Riverton CWA. If I overlay the 600 millibar temperatures here in white, it gives us a general idea of the band orientation, and it looks like the forecast from the ADA is for the bands to be approximately east-northeast to west-southwest oriented. Now I'll advance forward in time, and you can see that signature for the potential for mesoscale banding exists for some time during the day on the 30th, and for those bands to be just about east-northeast to west-southwest oriented for much of the day as well. So it looks like we also have the potential for mesoscale banding and therefore locally heavier snowfall amounts due to that as well. Next, I want to show a cross-section that goes from Casper, which is right here, over towards the Big Piney area right here. Notice the middle of it is just south of Riverton, and it does go through this mountain range right here. Here's that cross-section I just described, and what we're looking at here is isotherms in the dashed brown, winds, and also omega, which is shaded. And notice right in here, we actually have this cool pocket that just evolved. Actually, it evolved in time here as we look at the model forecast, which I don't show here, but this cool pocket did evolve in time due to precipitation processes and frontogenesis and all these factors coming together. One thing that does contribute to here is increasing the lapse rates in this region here as well. Also, since we're cooling to about -15 or -16, that's favorable in terms of dendritic growth. And keep in mind we have upward omega forecast in that same region as well. So favorable cloud microphysics for heavy snow, as well as upslope flow, fairly deep. Remember, we had northeasterly flow, and you can see that's pretty good upslope flow for this area. Also, look at the wind profile. We go up to about 500 millibars at the top of this map here. So we go from northeasterly flow and abruptly go to southwesterly flow. That shear profile is conducive for the mesoscale bands to be quasi-stationary as well, which of course would lead to locally heavier snowfall amounts. Now let's look at the surface observations, and as I go through the day here on the 29th, the day before the event, I want to highlight the approaching cold front coming through north-central Wyoming, like shown here, coming into this region. And then by the evening or late afternoon hours, we can see that cold air starting to make it towards Riverton's CWA here, like so. Now let's go to the water vapor imagery. I'll speed this up a little bit. And this is during the early morning hours to the late afternoon hours on the 30th, in other words, the day it's happening. And remember, we do have that jet that's forecast right across the area. I'll go ahead and throw on the 300 millibar ice attacks here to show that there is a pretty good correspondence between the jet streak from the ADA that morning. And we can see that lines up pretty well with the colder cloud tops here across Wyoming into Montana. And then if I take those off again, notice the development of a baroclinic leaf here about the early or first half of the loop here. And that actually corresponds pretty well with that approaching shortwave. It's pretty subtle here, but remember, we saw it initially on the water vapor imagery that I first showed as it moved into Oregon. It moved slowly across Oregon into Idaho and then towards Montana here, and that definitely appears to play a role here in terms of intensifying the system. Now let's go to the radar reflectivity, half degree from Riverton's radar, which is right here. And initially we see that cold front come in, like I showed in the OBS earlier, and we see the snow break out soon after that. Casper, which is right here, actually starts off as rain but quickly changes over to snow, and we can see the snow start to break out here. Also notice right here at Big Piney they're reporting snow, but there's no reflectivity. Keep in mind they're suffering from beam blockage because of this high mountain range right here, effectively blocking Riverton's radar from seeing that here. Now let's go to the IR imagery overlaid with the 300 millibar ice attacks here. And again, we saw this area in the water vapor imagery before, the colder cloud tops associated with the jet, as well as the low-level frontogenesis taking place and the favorable cloud microphysics and so forth. Also, another important thing I want to point out here is by late in the day, we start to see these clouds look like so, like I just drew in here, and they look pretty much east to west oriented, right about here. So I'll stop the loop, go to that time, and you can see they're pretty much east-west oriented, whereas these over here are southwest to northeast oriented, pretty much with the flow. And what we're seeing here is transverse bands associated with the jet streak. Those are pretty common in terms of when you see those with a pretty strong jet streak, and you can utilize that information you see in the satellite imagery to help you identify the existence of a jet streak. In this particular case, it lines up pretty well with the model output, but say if you're looking, for example, over the ocean or over a data sparse area, you can identify these jet streaks here by looking for these transverse bands in the IR imagery, and that helps you identify if the model is on track or what the effects of this jet streak may be. In this particular case, it's actually pretty heavy snow underneath this. Now let's go to the visible imagery for during the day on the 30th, and what I want to do is stop the loop and highlight that early in the day we see these cloud fields pretty much oriented from southwest to northeast, parallel to the upper level flow here. And then as we get later in the day, as we go towards evening, we can see these transverse bands by the evening hours, pretty much like so. And again, this is the perspective we have from the visible imagery. I just showed you the IR imagery here. And there's pretty heavy snow associated with that. And again, this is a sign of the upper level jet streak here, that we have these bands nearly perpendicular to the flow here as it comes in. Now let's go to the half-degree radar reflectivity loop from Riverton during much of the event here, and just highlighting that this was indeed an event that gave a pretty large area of snow over a fairly large area. Keep in mind they do suffer from beam blockage over here, and you can see they are reporting snow for a period here, so this does continue over to this area as well. And in terms of the locally heavier snowfall amounts that we were concerned about areas of upslope flow, which would favor higher snowfall amounts. And indeed, it looks like the east-facing slope of the Wind River Range right here has pretty persistent high reflectivity, supporting that upslope flow is definitely playing a role here. Also, we were concerned about mesoscale bands, and you can definitely see those here, approximately northeast to southwest oriented. Pretty persistent. Remember the shear profile being favorable for these bands to remain pretty much quasi-stationary, and indeed these bands were quasi-stationary and led to locally higher snowfall amounts within those bands there. Here's the snowfall map, and you can see over a pretty large area, roughly 6 inches over a pretty large area of Riverton CWA. But then you see these locally higher snowfall amounts here, like right here, 14 inches and 19 inches, close to the Wind River Range where we have favorable upslope flow. Also, we see pretty high values over here at Casper, 18 inches, and that would be right in those mesoscale bands that were persistent. And again, therefore, we see two factors here that led to locally heavier snowfall amounts. One, the mesoscale banding, and then two, the persistent upslope flow regions. So in summary, we looked at the position and intensity of a pretty strong jet here. Topographic effects played an important role in terms of upslope flow, as well as blocking out the radar, depending on what direction you're looking, and also mesoscale banding, leading to locally heavier snowfall amounts.
Now we'll be moving out to the western United States area, into the Medford CWA. This is a case from the 28th, 29th of December 2003, and we're going to be forecasting for the next 48 hours beginning on the morning of the 28th of December. The objectives in this case are going to be for tracking coastal lows and comparing them to the model output. We're going to be looking for mesoscale air mass characteristics. We're going to be focusing a little bit on the topographic effects and seeing how geography plays a role in precipitation production. And we're also going to be looking for multiple cloud decks and different techniques used to see these multiple cloud decks. Here is some water vapor imagery from 11Z on the 27th of December that runs through 14Z on the 28th. Basic or perhaps in-stream cyclogenesis is developing in the eastern Pacific and moving towards the west coast, as we can see right here. Another area we want to see the shortwave moving into southwestern area of Oregon right here, which is our forecast area. We've got a good fetch of moisture also moving in from the west. And another feature that we want to pay attention to, even though it's not doing anything at the moment, is this vorticity center up here in southwestern Canada, which is moving into the northwestern part of the United States into the Washington area. Here's the ADA 500 millibar height and vorticity analysis from 12Z on the 28th of December. We want to start off first noticing the strong northwest flow into Oregon, and it's forecast to move east during the day. We also want to notice that the cyclone coming in from the eastern Pacific towards the coast looks strong, but then opens up and weakens with time, and the vorticity maximum that was up here in British Columbia has now begun to take over and dig down the backside of the trough, slowing the trough down and increasing the amount of moisture and time that it's going to remain over the area. The vort max, as it moves south from Washington, does intensify and will probably play a more dominant role in amplifying the trough and in modifying the weather over the next 24 to 36 hours. Now we're going to look at the infrared satellite loop with the boundary layer winds overlaid between 1430Z on the 27th and 1730Z on the 28th. As we loop through, we notice the boundary layer winds are fairly well correlated with the low-level cloud streets. We also want to notice that the cloud streets in the warm sector off the California coast, as well as the cellular clouds off the British Columbia coast. Those are very important for looking for the difference in air masses moving into the area. The satellite, combined with the model output that we saw before in the boundary layer winds, can give us a pretty good idea of how well the model is doing. And in this case, the model's handling things fairly well. It's giving us at least a good trend of what is supposed to happen. And now we're going to look at the Medford terrain. We want to notice some of the more important topographical features in the area that may play an important part in the weather and the type of weather they receive in certain areas. Right here along the California-Oregon border are the Siskiyou Mountains. The Klamath Mountains run north-south right in this area. To the east of the Klamath Mountains is the Scott Bar Valley, with the Scott Bar Mountains north-south just on the east side of that valley. We've got a larger valley. The Shasta Valley runs right in through here, with the Cascade Range running down north-south to the east of it. Typically, these mountain areas in the area receive relatively high amounts of precipitation, while the areas downwind, if you get westerlies blowing in here, receive very little in the way of precipitation. However, there are certain situations that we want to keep in mind, and that is, what if cold air finds its way into the valleys and remains trapped? What effect would this have on to the typical weather scenario? Would it modify it? Would it increase precipitation, decrease precipitation? That's something that we're going to want to look at closely as this case evolves. And now we're going to look at surface observations taken between 5Z on the 28th and 14Z on the 28th. As we step through, we can see relatively cold temperatures and calm winds in the Sacramento and Shasta Valley areas, which are right through this area that we looked at previously. We also want to notice how the dew points stay at or below freezing in various locations in the CWA during this period of time. We want to think about what this can tell us, especially this area where we see fog formation right through here, the southern portion of the Shasta Valley. Now we're going to be looking at the ADA surface pressure, QPF, and wind fields forecast that were initialized at 12Z on the 28th. As we move out through time, we want to notice how the low pressure associated with the large cyclone off the coast begins to affect the CWA at this time. We can see it moving in and a large QPF field also moving in. We also want to notice another thing as we move out in time, this area down here with high pressure over the central portions of California moving up into the valley area. And this is into an area where the temperatures were already cold. What is that going to mean to us later? Now here's a fog product taken between 3Z and 9:30Z on the 28th of December with METARs overlaid. And as you probably already know, this product is made by differencing the 10.7 micron and 3.9 micron channels. As we loop this through, we'll see that in this particular case, stratus and fog are white, ice clouds are black. We want to notice particularly the light area which develops in the Shasta Valley in northern California. As time goes on, this area becomes larger and more well-defined. Note that none of the METARs are within this region, however. We looked at the cloud base observations for the nearest stations and found that they measured at around 700 feet. Therefore, we're looking at a stratiform cloud area which increases in aerial coverage throughout the night. Now, I'm going to increase the animation speed here and rock it back and forth, and you'll notice how these areas stand out a lot better here in the valley area. You can see the increase in aerial coverage, and it really stands out a lot better, and this is a really good tool to use and a good way of seeing multiple cloud decks. If you also look closely, you can also see some stable wave clouds up here through the southern and southeastern portions of Oregon. This would be inferring that we've got a relatively large stable air mass that runs all the way through this area. Now we're going to be looking at a loop of visible imagery taken between 1630Z and 2315Z on the 28th. First, we're going to look at this at normal speed, and we see embedded convective cloud tops moving into northwestern California, in this area right through here. We can also, based on the position of the low out here, assume that the ADA is doing a reasonable job in this case. We also want to look at something else as the warm front moves from here all the way into southern Washington by the end of the loop. Next, we're going to take this and we're going to increase the speed of the loop, and we're going to rock it back and forth and see what we can see. This technique allows us to identify persistent low-level features that are partially covered by higher clouds at times. What two low cloud features can you see in this loop that suggest a stable air mass that's trapped in the valleys and not mixing out at this particular time? We can see areas of the stratiform cloudiness that we noticed in the fog product before, right here through northern portions of California and the Shasta Valley area, and we can also see the stable wave clouds over here over the southern and southeastern portions of Oregon. Both these things suggest a rather large area of stable air right in this area, and that it's not mixing out at this time. What is this going to mean to the forecast? Now we're going to be looking at the 10.7 micron imagery that runs between 21Z on the 27th and 2030Z on the 28th of December. As we loop through, we notice the cyclone is developing with a well-defined warm conveyor belt out ahead of it, and it also appears to be occluding near the end of the loop. If you notice right through here, we get an occlusion process beginning. We also want to notice the cellular convection moving in off the coast into Washington, the cool air area off the Washington, British Columbia coast. This cold air never really makes it onshore, but is offset by the low-level warm air advection caused by the approaching cyclone in this area and pushes it up and out of the area. Note the surface low is still well offshore, though, at this time. We want to also notice that at the end of this, the surface low, with the cusp remaining in here, the surface low is going to be approximately in this area directly to the east, if you remember back to a cyclogenesis course. Now we're going to be looking at the half-degree reflectivity taken between 1840Z on the 28th and 5Z on the 29th. As we loop through, we're going to notice this area, the valley area, the Shasta and Scott Bar Valley area that we were looking at before, has enhanced reflectivity and very heavy snowfall at times, with very heavy snowfall also over the Scott Bar Mountains, which were just to the east of the Scott Bar Valley. It also should be noted that the town of Wairika in this area, which normally has light snowfall, due to downslope winds in the valley, recorded 23 inches of snow in this case, which was an all-time record. In this particular case, one of the reasons for this was because the cold air was trapped with stable air below, and we never really had good downsloping taking effect. We had an enhanced area of lift and therefore enhanced precipitation taking place through a rather cold, stable boundary layer, which enhanced the precipitation and snowfall. And now we're going to be taking a look at another half-degree reflectivity loop that takes place from where the last one left off, and that's 5Z on the 29th, and it runs through 23Z on the 29th. We want to notice the enhanced precipitation continuing over the Scott Bar and Shasta valleys. Note the precipitation continues, and the precipitation was slow to end partially because there was a secondary maximum precipitation which began early on the morning of the 29th. This may be a small unanalyzed shortwave that we will look at in the next water vapor loop. Now here is the water vapor imagery taken between 14Z on the 28th and 23Z on the 29th. As we move out, we first notice that the worm conveyor belt does eventually move east to the Medford CWA area. However, if we go back in the loop again, we want to notice a few other things happening. As it moves forward in time, we begin to see another shortwave ejecting into the southwestern portion of Oregon right there, which greatly enhanced snowfall and also prolonged it during that period of time. We want to move a little bit further ahead, and we notice baroclinic leaves developing along the upstream side of the trough right through this area, which also prolonged the snowfall and precipitation entering the area. And then finally we want to look at the shortwave that was up here in the British Columbia area as it moved down the backside of the trough, deepening and elongating it, and most importantly, slowing it down, which brought, of course, enhanced and prolonged snowfall. And here's the snowfall map from the area with terrain. Deep snowfall occurred over both the high terrain and the open valleys in this particular case, with a wide area of 15 to 20 inches throughout the valleys. And again, Wairika received 23 inches, which was an all-time record. And again, this happened because we had an area of stratiform, stable, cold air mass trapped in the valleys, and we didn't get the downsloping we would normally get in that particular case, so we had prolonged area of uplift and thus prolonged area of precipitation and snowfall through the cold air. In summary, we want to pay particular attention to the position of the coastal low on satellite, and that with the models, so that you can use them to verify the position. Also take into account the mesoscale cold air that was trapped in the valleys, and the tool that we used by speeding up the loop and rocking it back and forth in there to see these multiple cloud decks and identify the area of stratiform cloudiness. We also want to pay particular attention to the topographic effects that were minimized by the cold air that hung around the valleys and minimized the downsloping. And now we're going to be moving off to the central portions of the United States for a case that took place between the 8th and 10th of December 2003, particularly in the Missouri area. The objectives for this case will include cyclogenesis evolution on satellite, what type of cyclogenesis is occurring, looking for short waves, and we're going to be looking for the development of the trowel, which was talked about earlier in this session. Here is the ADA forecast, 500 millibar height and vorticity from 12Z on the December 9th. As we loop through, we notice a large amplitude trough located over the high plains is forecast to move eastward and deepen with time. Notice that the vorticity center over southwestern Texas Panhandle is forecast to move eastward and then northeastward towards Missouri. The potential vorticity advection associated with this vort center seems to correspond with the developing convection in the secondary warm conveyor belt that we'll see coming up in the water vapor loop. Here is some water vapor imagery from the period 9:15Z on the 8th of December to 17Z on the 9th. First, we notice the developing upper low over the Intermountain West and its track into western Texas by later in the loop. The track is something like this. We also notice that the low is disconnected from the warm conveyor belt out in front at the time, and this is a classic example of cold air cyclogenesis. Now, looking into the subsynoptic, we notice two things happening ahead of the developing low as we move back in time. We see a jet streak or shortwave moving out of the southern plains of Texas at 3Z. We see it moving into western Oklahoma by 7Z, and then into central areas of Kansas by 12Z. At the same time, we also notice the development of a baroclinic leaf and the beginning of upward motion over the Missouri area. By the end of the loop, we notice a couple of important features. We notice the destabilization of the air mass over eastern Texas ahead of the shortwave right in this area, and the development of thunderstorms. And at the same time, we also notice the development of the secondary warm conveyor belts. Both the shortwave and the development of the secondary warm conveyor belt now suggest instant occlusion cyclogenesis, with the convective development in the secondary warm conveyor belt implying advection of unstable air towards the surface low, which is now just east of the cusp, right in this area over extreme south-central Kansas or north-central Oklahoma. And this means that the low is deepening very rapidly. Here's the mesoADA sea level pressure, temperature, QPF, and surface forecast from 12Z on the 9th of December. The surface low talked about previously is shown to move from northeast Oklahoma towards St. Louis and deepen with time. Also note the strong thermal advection on either side of the low. The freezing line moves across Missouri, just behind the surface low, and there's a large area of 0.5 to 1 inch per 6-hour forecast to fall in the area that is below freezing. This suggests that the precipitation will begin as rain and then change over to snow. Also notice that by 9Z on the 10th, you can see wraparound precipitation developing to the northeast of the low. This will be shown to be the trowel which overrides the cold air and brings snow to most of western Missouri. Now here's the mesoADA forecast sounding taken from near Columbia, Missouri, starting at 12Z on the 9th of December, running out about 30 hours. Initially, the lower levels of the sounding are well above freezing, and the sounding is quite unstable. This unstable air is where the secondary warm conveyor belt is filling in. Over by 6Z on the 10th, we see the wind shift to westerly, and by 9Z, the temperatures become cold enough for the precipitation to change over from rain to snow. Early in the period, we observe the winds veering with height, warm air advection, and after the wind shift, the winds are backing with height, cold air advection. Here is GOES 12 water vapor imagery from between 14Z on the 9th. It runs through 23Z on the 9th. It's overlaid with the ADA 500 millibar height and vorticity field. As noted earlier, when the shortwave approaches the warm sector in eastern Texas, there's a sudden development of convection in the warm conveyor belt. The shortwave was indicated on the ADA 500 millibar forecast, and this example illustrates the utility of combining satellite imagery with model output. The model analysis in this case leads us to expect a shortwave, and the satellite imagery confirms the shortwave's existence and gives us a better definition of time and space. Also notice in both the satellite and model analysis the strongly diffluent shear region ahead of the upper low. Here's GOES 12 10.7 micron imagery from between 245Z on the 9th running to 1Z on the 10th of December. We can see stratiform clouds associated with the post-frontal precipitation moving across Oklahoma and into Missouri. Also, early in the loop, we'll notice that the cusp with the upper low in western portions of Kansas right here puts the surface low roughly in north central Oklahoma at this particular time. As we move forward from this period, instant occlusion takes place and a second cusp forms over central Oklahoma by around 20Z. If we look at this time, we have the cusp right here and the low just to the east over northeastern Oklahoma. Again, as the vorticity center approaches the warm conveyor belt of the primary system, convection begins to wrap around back into northeastern Oklahoma. And when the occlusion process begins, the trowel forms as the cusp turns eastward. Stations, it must be noted, in northeast Oklahoma reported 6 to 8 inches of snow at this time. Here is additional GOES 12 water vapor imagery from between 18Z on the 9th of December and 14Z on the 10th. We can see the system continuing to move rapidly to the northeast, but the cusp remaining over Missouri by the end of the loop. The precipitation associated with the cold conveyor belt and trowel is still occurring, and during the second half of the loop, we can see the warm conveyor belt wrapping around and maintaining the feed of moisture into western Missouri. Here is some GOES 12 10.7 micron imagery taken between 7Z and 16Z on the 10th with METARs overlaid. By overlaying the METARs, we can see that the rain-snow line is entirely associated with the north-south band advancing eastward with the elongated cusp. There's lots of overrunning moisture and precipitation, and the snow region is situated entirely behind the surface low. This is not always the case, but for this example, we can use this satellite feature to track the rain-snow changeover. There was 10 to 14 inches of snow in portions of southwestern Missouri. Here's a radar reflectivity mosaic taken between 0Z and 21Z on December 10th with METARs overlaid. It's a review of the entire event. We can see early convection associated with the warm air advection and secondary warm conveyor belt, and then we can also see the wraparound precipitation that appears as the trowel develops. By utilizing satellite imagery to define the larger picture, in this case we can better understand the evolution that we observe on radar and match it to the forecast in the models. Here's a quick look at the 24-hour snowfall map ending at 12Z on December 10th. We see a large area of 4 to 6 inch snows right through this area in southwestern Missouri with an enhanced area of 10 to 14 inch area in extreme southwestern Missouri. In summary, this is not only a good example of cold air cyclogenesis, but also of instant occlusion cyclogenesis. We also wanted to note the role of the short wave and the jet streak in the occlusion process, and also the short wave and jet streak's role in convection in the warm sector, and the development of the secondary warm conveyor belt and subsequent system intensification. We also followed the development of the trowel and noted that the snow occurs in the region of wraparound precipitation in the cold air sector behind the low.
Here's our last case study from 10 to 13 December 2003, and we'll be forecasting for the area shaded in here with a special emphasis on Tulsa, Oklahoma, which is right about there. Our objectives here are to follow a cyclone and its evolution, and most importantly, look at the precipitation type forecast here. We'll start off with the water vapor imagery, and three important things to point out here. One, we have a subtropical jet across Old Mexico extending into southern Texas towards Louisiana. We have an Arctic trough coming across the northern plains moving towards the south. And then the feature that would play a role here in terms of precipitation towards our forecast area is this short wave moving out of Arizona into New Mexico and heading right for Oklahoma, Texas, and right towards our forecast region here. We'll start off with some model output, and this is the Ada 500 millibar heights in green, isotherms in dash salmon, and then vorticity is shaded here. Here's that short wave across Arizona, and what we'll do is follow it along in the forecast time as it moves into Texas and then into Oklahoma. Notice on the back side of this low, the temperatures aloft get pretty cold, and keep in mind I already told you this is going to be a precipitation type forecast problem. So on the back side we do see those temperatures aloft cooling, and of course that could help change it over to snow, as I'll show in a little bit here at the lower levels. First, let's look at the surface analysis from HPC. We see a low across western Texas with a warm front extending northeastward towards the Dallas region, and then to the north we have a cold high pressure system. So the forecast, as I'll show in a minute here, is for this warm front to move towards the north into Oklahoma, towards that colder air, and the big question being where the rain-snow line will set up. Now let's go to the Ada forecast MSOP in green contours, isotherms in the red contours here, along with the winds, and QPF will be shaded. Going along in the forecast time here, keep in mind the low is pretty much towards the south or southwest during this time. Warm front stretching towards the northeast, forecast to move into Oklahoma, something like that. And we can see the precipitation associated with it as I move along here. And then on the back side of the system here, we see this region of precipitation, also colder temperatures. Keep in mind the 500 millibar temperatures that I showed earlier with that column cooling. It looks like it's cold enough for snow here on the back side. So looking specifically at Tulsa, looks like early on the precipitation moves in, and they're very close to the freezing mark here. So the big question is will be where that rain-snow line sets up, and then it looks like by later in the event it will definitely change over to snow. This is a precipitation type problem, so let's look at some soundings. Here's the Norman sounding, and I'll go ahead and draw the zero line in to make it more clear. And the warm layer here is pretty significant, about 7 degrees Celsius or so. And even though it is below freezing at the surface, it's a very shallow cold layer. And this is also a 12Z sounding as well. So this looks like a rain sounding here with some possibility of freezing rain, but it will be warming up here shortly after 12Z. Let's go further north now to Springfield, Missouri. And you can see this is definitely a snow sounding at this time, with the temperatures definitely below freezing at this particular time. So Tulsa is about midway in between these two soundings, so the question is where does the rain-snow line set up? So let's look at the satellite imagery to see if we can get any clues here as to where that rain-snow line might set up. Let's go to the water vapor imagery here, and you can see our approaching shortwave and the precipitation associated with it as it goes into Texas, Oklahoma, and Kansas. But the thing I want to emphasize here is the convection that we see developing right here in eastern Texas. And what can we infer from this convection that we see here in eastern Texas? Well, a couple things. First of all, we can infer something about the cyclogenesis here. Keep in mind this is pretty much a warm conveyor belt down here across Old Mexico into southern Texas into Louisiana. So therefore, when you see convection developing between the warm conveyor belt and the low back to the northwest in this particular case, you can deduce that this convection may be leading to a secondary warm conveyor belt, which would help advect unstable air into the system and help that low to develop a little more rapidly. Now there's one other thing you can deduce in this particular case, since we're concerned about precipitation type. You can also say that we have this unstable air here by the fact that we have convection, and that unstable air could advect northward into our system and help advect that rain-snow line further northward. Let's look a little more closely now. Here's the IR imagery, and I overlaid the 850 millibar theta E here, and indeed that convection right here in eastern Texas is associated with a theta E ridge, so we have a ton of unstable air here, and you can see it pointing towards the north. One other thing I want to point out, if I stop the loop, I want to draw in some low clouds here that we see from Arkansas into Oklahoma, extending something like this at this particular time. And then as we go later in time, you can see that the cloud line right here in Arkansas didn't move a whole lot, whereas in Oklahoma it moved northward pretty rapidly. So what we're seeing is warm sector air here being advected northward quite rapidly across Oklahoma, whereas in Arkansas it's not moving a whole lot towards the north. So this will help move that rain-snow line northward here in Oklahoma, and you can see it looks like it's going to change over to rain here in Tulsa as this rain-snow line moves towards the north with this unstable air pushing it pretty far to the north. Now let's look at the IR imagery zoomed in right over Oklahoma here and overlaid with the odds. What I'll do is stop the loop, and you can see early on here, this is 2230 UTC, so late in the day, and we can see the effects of that unstable air moving rapidly northward, that indeed it was a changeover to rain here, and it was quite warm pretty far to the north here in eastern Oklahoma. So that helped change it over to rain and keep it warm enough for rain here. Meanwhile, just northwest of that line where the temperatures are colder, you can see it's snowing. And what I'll do is just advance forward in the loop here. And you can see this precipitation moves off towards the northeast here. And then we see this next round of precipitation right here move across Oklahoma, and with it we can see colder temperatures. Recall again the 500 millibar temperature forecast to be colder in this region, and therefore it looks like we have some column cooling. And as this moves across the state, you can notice here at Tulsa it goes from 35 in light rain, and it changes over to snow as the temperatures cool down a little bit as well. So to summarize here, we found that this unstable air is moving pretty rapidly towards the north here in eastern Oklahoma. It helped keep it for a period of rain until this came along, and column cooling resulted in snow as this moved across the state towards the northeast. Going back to our water vapor imagery here, remember with the convection we had been analyzing there over eastern Texas, and it actually dissipated. It didn't make it into Louisiana and Arkansas. Remember that unstable air didn't go too far to the east, so as that convection moved to the east here, it ran into that stable air, never really got going. It failed. So therefore that secondary warm conveyor belt never really got going, and therefore this low wasn't quite as intense. But For the time that we did see it here in eastern Oklahoma into, or I should say extending from eastern Texas into eastern Oklahoma, it was enough of a push here to help move that rain-snow line enough towards the north, pretty close to the Kansas border, and also keep Tulsa in rain for a period of time until we saw this wraparound portion of the low come along with its cooler temperatures and change it over to snow for some period before it eventually ended the precipitation. Here's the radar mosaic, and what I'll do is just overlay the observations here. And again, the early precipitation being in the form of rain moving off towards the northeast, and then we see this wraparound portion of the low come along and change it over to snow by later in the loop here. Here's the observed precipitation. You can see hints of that convection there in eastern Texas, which led to higher rainfall amounts down there. Also, you can see quite a bit of precipitation here in north central Oklahoma and then into Kansas. Next, we'll look at the snowfall map. Here's the snowfall map, and here is what the result of that rain-snow line being pushed further northward by that unstable air mass that we saw moving towards eastern Oklahoma. And the effects it had here are pretty clear, that it kept this area snow-free. It kept it in terms of rain for quite a period of time. And then the heaviest snow being just northwest of that, up to 10 inches of fell here in north central Oklahoma. Summarizing the case here, we looked at a cyclone evolving an attempt at a secondary warm conveyor belt, a narrow stationary theta E ridge, and the warm sector, we could identify it and track it along here, and it helped change the precipitation type over to rain in eastern Oklahoma for quite a period of time until finally the wraparound portion of the low came along and changed it over to snow. That concludes this training session, just summarizing here that the role of satellite data in winter weather forecasting can be critical in evaluating the synoptic and subsynoptic pattern, and also in updating your forecast precipitation amounts by utilizing that satellite imagery to identify where and also when. Utilizing both model output and satellite imagery in tandem can result in a better forecast than one prepared using model output alone.